In this tutorial, we are going to calculate the density of an organic molecule using molecular dynamics. We are going to use GROMACS as the molecular dynamics engine, and we're going to visualize everything using PyMol, so you might want to install those software first. We will also need AC pipe to generate the parameters of the molecule. So first, I have already created the molecule we are going to simulate, which is cinnamaldehyde. So we can open it up in PyMol. One thing to note is that I have represented the bonds in the benzene ring here as double and single bonds instead of just delocalized bonds. You need to do this in order for the molecule to be passed by AC pipe correctly. Otherwise, it's pretty standard to just build the molecule in any software you want. You just have to save it as a .mol file. So next, we are going to generate the parameters using AC pipe, which is this software. We use the command -i and then the name of the file, which is the cinnamaldehyde.mol, and this will generate the parameters. In this case, the molecule is neutral, otherwise you have to specify the charge. Now it's done. We can see we have a new folder, which is the cinnamaldehyde.ac pipe, and this folder will contain all the parameter files for different software. In our case, we are going to use the _GMX files, which are made for GROMACS. So let me just copy the GRO file. This is the structure file in the GROMACS format. Cinnamaldehyde here. And then the next file we need is the .itp file, which is the parameters for the force field, which is the amber force field in this case. So just rename this here. Now we have all our files in the same directory. We can start preparing the molecule for the simulation. First, we need to prepare an initial box containing all the molecules we want to simulate, and this requires us to put a small box around the molecule for the replication to a larger system. So we're going to make a little box around the cinnamaldehyde, then copy it a certain number of times to make a big box, and then we're going to simulate that box and let it relax to its final density. So how we actually do this? We use first the command gmx to call GROMACS, and then edit conf. This will put the small box around the molecule first. So we're going to -f and then the structure, cinnamaldehyde, and we're going to output, so -o, to a unit box. And then we need to specify the size of the box, and since we don't really know exactly the density, I mean that's what we want to calculate, we're going to put 1 nanometer around it, which is pretty large, but during the simulation the density will converge towards the calculated density. So now we have our new file, which is unit box. We can open it up, but it looks exactly the same because the box actually isn't shown here, but in the file, actually if we open the file, we can see in the last line there's a 1.0, which is the size of the box, which is going to be read by GROMACS. Next, we are going to copy this box into a larger system, which we will actually simulate. So gmx genconf and then use our unit box and output this into a box. And then the commands here are parameters for the generation, so we want to rotate randomly the molecules so we don't have something too symmetrical, and we want to copy this box 5 times in every axis. So we're going to have 125 cinnamaldehyde molecules in total. Copy this. Okay, open the box, and we see all the molecules here randomly rotated, and they don't overlap, so there's not going to be any clash which might crash the simulation. So everything looks fine. close this. And now the first step is to relax the system using the energy minimization calculation. So I have here the em.mdp file. For this purpose I have chosen some parameters. They can be different in your case depending on how precise you want to be. We also need a topology file. So here I have prepared the topol.top, which is very simple. So we first include the force field we want to use, so the amber force field. We also include the parameters for the cinnamaldehyde. Here we give it the system a name, which is not that important, and specify how many molecules of cinnamaldehyde we have. If you change the name of the input file, of your .mol file, you will need to change this line to have exactly the same name. So we see in the cinnamaldehyde.itp there's a molecule type name here. This needs to match the name in the topology file. So now that we have that, we're going to minimize the energy. So call GMX grom to prepare the file using the MDP file for the minimization. I'll put em.tpr, use the topology, use the box, and then we have our em.tpr file. We just need to run the simulation. So to run the simulation you do gmx md-run, and then the parameters will change depending if you want to run the simulation on CPU or GPU. In my case I will use the GPU, so I'll use one MPI thread, df, and we're going to add -v to have the verbose mode, which is going to tell us how much time it is going to take in real time. So the simulation was really short, and then we should have a em.grow file, which is our minimized file. So it looks pretty much the same, but it minimized the energy, so we have a relatively stable system to start with. So that's perfect. Now the next step is running actually the simulation. So I have the md.mdp file, which has some different parameters. Once again, the parameters can change depending on your settings. The most important part is the number of steps and the time step. So I have a 2 femtosecond time step, and I'm going to run for 4 nanoseconds, which is going to be enough for the system to equilibrate. So we can exit out of that. Then again, prepare the simulation, grump md.mdp, I'll put a md.tpr file using the same topology. Now using the minimized structure, so em.grow, that we just generated. Now we have the md.tpr file. We just need to run the simulation, just exactly the same command, except we change the name of the file. So instead of em, it's going to be md. Verbose mode, and this might take a while, so I'll speed ahead. So now the calculation is done, so we just need to analyze the results. So we have some new files. First we'll look at the last frame of the simulation, which is the md.grow. We can see all the cinnamaldehyde molecules are all very close together, so at equilibrium, and they should have the true density of the liquid. Next we can look at actually the simulation. So we open up the first frame we used, and then we load trajectory, which is the md.trr. We load all of this, and we can play the simulation like this, and we're going to see that the molecule will get closer together and equilibrate into a nice uniform liquid like this. And now we just need to calculate the density, so we can use GMX energy, feed it the EDR file here. Then we have access to all the properties of the simulation. We want density, which is 22, 0. Then we have a new file which is called energy.xvg. You can open this up, see the calculated density in function of time. So we go on, the density increases greatly, and at the end it's about 1.04 grams per milliliters. You can plot this. There's no real program to do this already in GROMACS, but you can write your own script. So I have my script here, energy.xvg, like this. So we can see the density starts very low, so that's because we used a big box around all the molecules, so they're all spaced apart. But as the simulation goes on, we see the density increases until this point where it's pretty stable. So we're going to discard everything below 4 nanoseconds as just equilibration, and then take the average value over the other 4 nanoseconds of simulation. So to do this, we do the same GMX command here, energy, where we specify -b for beginning at 400 picoseconds, and then output the density once again. And we have here the statistics, so the average value in kilograms per meter cubed, and we have here the error estimate here. We just have to convert this into grams per milliliters, which is simply by dividing by a factor of 1,000. So the true density according to the simulation is 1.035 grams per milliliters, which is pretty close to the true value of 1.05 grams per milliliters. So the simulation gives a pretty good estimate of the density of cinnamaldehyde here, while we have performed no experimental measurement. So this is purely from the force field, and different force field will have different accuracies, so you can experiment with different force fields and parameters to see which one gives the best results.